Here we go again, and we are discussing the periodic table and periodic trends. Last time we talked about how we could use the periodic table to figure out in what period and what group the element was, and then we talked a little bit about the periodic law, and we learned that we could predict how um, certain elements would react based upon the group in which they are placed, right? And so now let's move on to a very powerful aspect of the periodic table, and that is the idea of periodic trends, the trends that exist in the periodic table. So let's start here with the neutral sodium and argon atoms, which has a larger atomic size and why. So let's talk a little bit here about periodic trends. Periodic trends, okay? And so this would be a branch off of our main periodic table concept map. Periodic trends. Let's start over here and let's go with atomic size. Atomic size. And when we're talking about atomic size, we're really talking about what? The size of the electron cloud. That's what gives the atom its size. And here, the real question to me, I guess, is, what affects that? Well, when I think about what might affect my electron cloud, I think about the negative charge here, right? And I know what? That if I have a positive thing and a negative thing, there's an attraction between it. And that's what we have in an atom, right? We have the positive nucleus and we have a negative electron. And there is an attraction between these two. And in fact, there is something called Coulomb's law, which I'll tell you is the most important equation that you will never be asked to use in chemistry. You hear that? It's the most important equation you'll never be asked to use, but it explains so much. And here's what Coulomb's law says. It says that the force of attraction between a positive and a negative, or between positive and negative charges, is equal to K Q1 Q2 over R squared, where Q1 would be the charge of one body, Q2 is the charge of the second body. K is a constant, so we don't worry about it. And R is the distance between my bodies. Okay, so how does this affect us? Well, what's one of my charged body? We could say that Q1 is my proton charge, and we can say Q2 is my electron charge. So I have my proton charge and my electron charge, and R squared, well, that's the distance between my proton and my electron. Okay, so how do we interpret this? Hey, first of all, will my electron charge ever change? The answer is not really in this case, because my electron's always going to have a -1. But what about my protonic charge? I guess I should call this my nuclear charge. Not really my proton. This is my nuclear charge. Well, does my nuclear charge change? Well, as I increase my atomic number, my nuclear charge can increase. So that means this thing can go up. What about my distance? Well, we'll find out about my distance later, but as my distance goes up, my force goes down. Force of attraction goes down. Here, let me clean that up. So let's try to summarize this a little bit based on Coulomb's law. My force of attraction between my nucleus and my electron is going to go up with my increasing nuclear charge. Okay? Why is that? Because that means my Q1, right here, let's write this again, KQ1 Q2 over R squared equals my force. If my Q1 increases, what's going to happen? My force is going to increase. What else? Well, what happens if my distance increases? Well, if my distance increases, what happens? My denominator gets bigger, which means my whole number gets smaller, which means my force goes down. So as my distance between my proton between my nucleus and my electron gets bigger, that force of attraction gets smaller. Okay, that kind of gives us a background of what's happening in my atom. Now, to the specific question, let me talk about what affects my charge. Well, not a charge, what affects my size. First, let's look at across the periodic table. Across the P table, meaning from left to right. From left to right. What happens? Well, as I go across from left to right, let's look at my periodic table. What happens as I go across from left to right? What do you see? Well, first of all, they're all in the same period. That means they all have the same N, right? That means they're all in the same shell. So they're in the same shell. Good. So that means my size, well, let's not go there. So they're all in the same shell. But notice what's happening to my atomic number as I go from left to right. My atomic number increases. That means what? I have more protons in my nucleus. And that means what? If I have more protons in my nucleus, I have a greater nuclear charge. If I have a greater nuclear charge, what's that do to my force? My force goes up. And if I have a stronger force, is that going to pull my electron cloud tighter, or is it going to push it out farther? Well, with a stronger force, it's going to pull it tighter. So as I go across the periodic table from left to right, I'm going to have a greater force, so my atomic size is good. My atom is going to be pulled tighter, so my atomic size will decrease. And why is that? Like we said, increasing nuclear charge. Okay, so these are the two guys that I really want you to know. This Coulomb stuff, that's just for your basic understanding. So what is the trend? The trend is, as I go across the periodic table from left to right, my atomic size goes down. Why? Because my nuclear charge goes up. Good. So can we answer our question? Neutral atom of sodium and argon, which has the larger size. Here's my sodium. Here's my argon. As I go from left to right, I have greater nuclear charge, greater pull. So that means my argon is smaller, and that means my sodium is larger. And so to answer my question, the neutral sodium and which one has a larger, then my answer is sodium is larger than argon. Why? Because sodium has a smaller nuclear charge. Okay, and when you get into AP, we'll talk more about effective nuclear charge, but for the time being, this is fine. Good. Consider the neutral sodium and cesium, which has the larger atomic size. Oh, this should be easy, right? Sodium and cesium. Where is sodium? Where is cesium? Here's sodium. Where's cesium? Where's cesium? Where's cesium? Oh, cesium's down here. Well, they're not in the same period. Can I use that same rule? Nope, can't use that rule. We need a new rule because now I'm going down a group. So what's the rule when we go down a group? Okay, let's get our next trend. Trend number 2. In atomic size, as I go down a group, what happens? Well, as I go down the group, notice what's happening. My protons do increase, okay, but that's not the main thing that's affecting us here. I go from period 3 to period 4 to period 5 to electrons in period 6. And remember, as it's period 6, excuse me, shells. I have an electron and n equals 3 here. And I have an electron and n equals 4 here, and n equals 5 here, and n equals 6. So that would mean what? Here's 1, 2, 3, 4, 5, 6. So in my sodium, it's 1, 2, 3. I have an electron here. In my cesium, I have an electron way out there. And so what's the difference between these? The big difference here is distance. And remember what I said with Coulomb's law. As my distance goes up, the force of my attraction goes down. And if there's less force, then there's not as strong, the pull on the electron is not as great. So that means my my electron cloud is bigger. You guys follow that? The distance from the nucleus greater for cesium here. Okay, and if it's greater for cesium, that means there's less pull and my electron cloud is bigger. So what is the trend as we go down a group? Atomic size increases. Now, why is that? The main reason why is we are adding electron shells. And so that means what? Electron is farther from the nuclear charge, from nucleus. And what some people will say is a second reason is shielding. And that means shielding is other electrons pushing the electron away, core electrons pushing the electron under the farthest electron out. And what they mean by that is, let's say I have a nucleus here, and then I'd have a couple electrons in here, and here's the outer edge of my electron shell, right? Electron cloud. Well, this electron is going to be attracted by the nucleus, but it's going to be repelled by these two electrons because they're both negatively charged. So the net effect that this guy feels is he feels some negative from the electron, some positive from the nuclear charge. So the effective nuclear charge here is less. And we call that, as a result, that effective nuclear charge is decreased because of shielding. So part of the reason the size is bigger as we go down is shielding, okay? I think the main reason is we're adding shells. Got it? Okay, good. Let's see if we can do another one here. Oh, great. Here we go. Well, first of all, did I answer my question? The neutral sodium and cesium atoms, which has a larger cesium, why? More electron shells. And once again, how did I know that? Well, because remember the period for groups 1 and 2, the period for my S block indicates my electron shell. Good. Here you go. Consider gallium, germanium, cadmium, and indium. Which has the largest atomic size and which has the smallest? Pause me, and when you have an answer, bring me back. Well, let's find these guys on the periodic table. Let's get rid of some stuff here. We need to find what? Gallium. Well, let me go back and see. What is it? Gallium, germanium, indium, and cadmium. Gallium, indium, germanium, and cadmium. And cadmium, gallium, indium. Okay, there we go. So, which is the greater and which is the smaller? Well, first of all, we have two trends here. We have this trend and we have this trend, right? If I go from left to right, I'm getting smaller. And if I go from top to bottom, I'm getting larger, right? Okay, so let's start off here with gallium. Let's compare gallium to germanium. Well, I'm going from left to right, so germanium is smaller than gallium, so let's go like germanium is smaller than gallium, right? Why is that? Germanium has a greater nuclear charge. Now, let's compare gallium to indium. All right, gallium to indium. So I'm going down here. That means indium is larger, so that means gallium has to be less than indium. Now, what about cadmium versus indium? Well, once again, I'm going from left to right. Cadmium has to be what? Well, indium has to be what? Smaller than cadmium, so that means cadmium is over here. So, germanium is the smallest and cadmium is the biggest. Got it? Germanium is the smallest, and cadmium is the biggest. And how would I explain that? Well, I looked at germanium has the greatest nuclear charge, right? It was farthest to the right, greatest nuclear charge. And in terms of cadmium, cadmium had a lower nuclear charge than indium, and cadmium had more shells than germanium and gallium. Got it? So that's how I would explain that answer. Okay, cool. Let's move on. Consider sodium and sodium plus, which has a larger radius, or excuse me, which is larger. Why? Okay, so let's come back over here and let's build off of our atomic size. And let's kind of come over here and talk about the size of ions. Okay, and so what are ions? Ions are charged elements. That means an atom or an element atom with a charge. And what does that mean? That means the number of protons does not equal the number of electrons. Okay, now we really have two types of ions. We have cations, and that means they have a positive charge, and we have anions, and they have a negative charge. Now, what causes something to have a positive charge? Oh, I lost cation. What causes something to have a positive charge? Well, that means there are more protons than electrons. Aha. So that means I have more protons in my nucleus than when I have a neutral. Let's see, there's four. Let's just make it two. We'll make it easy here, right? Good. Now, this is a case where I have more protons, so this would be a +1. This is neutral. Which of these do you think is going to have a stronger pull on the electron? In this case, I have two positives pulling one electron. In this case, I have two positives, and it's pulling this electron, but this electron is pushing away from this first electron. So which of these is going to be the bigger one? Well, this is going to be bigger because it has a lower effective nuclear charge, lower effective nuke charge, and that effective nuke charge is changed because of the shielding, right? Since this electron is pushing off that electron, it has some shielding, which means this whole electron cloud will be bigger. This one will be smaller. Okay, so can we state a trend here with cations? Yeah, the trend with cations is the cation is always smaller than the neutral atom. And why is that? Because it always has fewer electrons. Good. And remember, cation is positive charge. What about on the anion? Well, on the anion, I have more electrons than protons. That means I've added an electron. So what do you think is going to happen when I add an electron? Well, my anions are always greater in size than my neutral atom. And why is that? Because we have added an electron, at least one electron. So those are the two trends. Anions are always greater than the neutral atom. Why? And cations are always smaller than the neutral atom. Good. Here we go. Sodium and sodium plus. Which is larger? Hey, sodium is. Why? Because Na plus has fewer electrons. And since it has fewer electrons, it has a greater effective nuclear charge. Effective nuclear charge. Remember, that means it has it feels a stronger force from the nucleus than the sodium does. Good. What about my chlorine versus, what's that? That little minus there? That means there is an electron added. It's chlorine versus chloride. Which is bigger? My chloride is always bigger. Why? It has more electrons. It has more electrons and the same charge, same nucleus, right? The same nucleus. Since it has more electrons, it actually has a smaller effective nuclear charge. Okay? Any questions about that? All right. How are we doing on time? Well, I think we ought to quit here, and we'll finish off periodic trends next time.